Welcome back to George Mason's Stat 250, Introductory Statistics 1. We will be working in Chapter 14 and 15, where we will be learning some inferential statistics techniques. We've done a lot of work to get to this place to where we're actually doing inferential statistics. So we're at a great place now. More specifically, we'll be learning techniques, if certain conditions are met, that will estimate and test a parameter value. When we estimate, we use confidence intervals. When we test a parameter value, we do a hypothesis test, or another way to say that is tests of significance. But before we get into how to do this, let's do a little bit of review. First, very basically, what's a distribution? Well, that would go back to talking about we need to understand what a variable is. And remember what we said way back when. We have a question that we want answered. The place in which we go to get that question answered, whether it be people, things, animals, whatever, we go to a population and we look at a specific characteristic that will help us, or characteristics that will help us answer questions. Those become our variables. And we learned variables could be qualitative, things that categorize, or quantitative, things that have a numerical basis where we could actually do arithmetic operations. And if it's numerical, we had discrete and continuous. Discrete meaning counts, continuous meaning measurements. With discrete, we have discrete values for our variable. In the continuous variable, we talk about interval lengths. And then we talked about, okay, great, so we have this variable. Now the variable will take on values. And we can look at which variable and how often it occurs. That gives us a distribution. So a distribution tells us the value of a variable or range of values of a variable. That's generally what we put along the x-axis. And how often, or the percent of time, that value or range of value occurs. That's generally found along the y-axis. And when you put these two together, we get a distribution. And we've seen many distributions and have studied two very significant distributions just recently. In Chapter 3, we talked about the normal distribution, and in Chapter 13, we talked about the binomial distribution. Sometimes people get confused because they look at Chapter 11 and think that that should be Chapter 3. In other words, that sampling distributions are somehow normally distributed. Not necessarily. Certain conditions would have to be met for a sampling distribution to be normally distributed. So in Chapter 11, we learned about this very special distribution. So what is a sampling distribution? If the variable is or was a statistics, such as the sample mean, the sample standard deviation, or the sample proportion for a set sample size. In other words, I go to the population, I take samples of a certain size, and I keep taking samples of a certain size over and over. But I do something to these samples. I calculate either the sample mean, sample standard deviation, or the proportion, sample proportion. And I collect all those sample means, sample standard deviations, and or sample proportions. The collection of those statistics together, that statistic is a random variable itself because I don't know what it is before I actually calculate it. So when I collect all those sample means, those become actual variables themselves. So they create their own distribution. How many times does a sample of size 10 have a mean between 12 and 14? So I create what's called the sampling distribution of a statistic. And we went very heavy in Chapter 11 to talk about the sampling distribution of the sample mean for samples of a specific size. We called n. N could take on one to whatever number. So we looked at that for the sampling distribution of the sample mean. And there's a very special relationship between the sampling distribution of the sample mean for samples of a specific size, n, and the population the samples came from, those samples of size n. That the mean of the sampling distribution actually equals the mean of the population, always. And that the sampling distribution of the sample mean for samples of size n, its standard deviation And we shorten that. We have a name for that. We call the standard error. So remember, the standard error is nothing more than the standard deviation of the sampling distribution. So the standard error of our sampling distribution actually equals the standard deviation of the population divided by the square root of the sample size. So if we know what the mean of the sampling distribution is, then we know what the mean of the population is, and that's where we're going to go in this chapter. Now in chapter 11 we always assumed we knew the population, mean, and standard deviation, and we were trying to find things out about the sampling distribution. That was to help us work within the sampling distribution. Now we're going to see why we even learned about the sampling distribution, and it's just this right here. We'll be working in sampling distributions, and we're going to estimate the sampling distribution's mean. And from doing that, we'll be able to estimate what the actual parameter mu is, because those two equal each other. So when we estimate the sampling distribution's mean, we're actually estimating the population mean. And if we know that what the standard error is, that is the standard deviation of the sampling distribution of the sample mean for samples of size n. Big mouthful, right? It's nice that we can say standard error instead of the standard deviation of the sampling distribution of the sample mean for samples of size n. We denote that with that sigma and its subscript of x bar. Then we know that what the standard deviation of the population is, what sigma is. It would be our standard error times the square root of n, and that should be a small n. So it should look like that. That this standard deviation of our population is the standard error times the square root of n. For the inferential techniques we're going to be looking into, we'll always be in the sampling distribution for a specific sample size. When we estimate the statistic, then we can use this we can use this to estimate the population parameter because of the relationship we just saw. If we need to test a value of a parameter, we will look at the sampling distribution for samples of size n and using that parameter value. So if the sample we have makes sense in the sampling distribution, we'll say we don't have enough evidence to believe the parameter value has changed in some way. But if that sample lands in the tail ends, in one of the tail ends or both or whatever, well, it would have to land in one or the other, this may be enough evidence to conclude the parameter has changed. And we'll see all this. I'm just kind of getting you ready for what's going to go on in this chapter. So what are we going to be doing first? And I gave a very, very sketchy reasoning of statistical estimation and testing, but we're going to get more specific into the reasoning of statistical estimation, margin of error and confidence intervals for a population mean, conditions for inference in practice, how confidence intervals behave, planning studies, sample size for confidence intervals, the reasoning of tests of significance. We're going to learn about how to state hypothesis, how significance tests behave, and remember, significance tests are nothing more than hypothesis tests. Type 1 and Type 2 errors, what are they? P-value and statistical significance, tests for a population mean, and significance from a table. Also, we're going to be using Minitab to answer these questions too, where Minitab does all the work for us, which is nice, but we have to interpret what Minitab is giving us and making sure all our conditions are met so that we can use Minitab. Remember, in statistics, you can always do a technique, you can always put numbers into a formula, but if the conditions aren't met, you can get an answer, but the answer is not reliable. So we have to be very, very careful that our conditions are met in order to do any of these techniques. So statistical inference provides methods for drawing conclusions about a population from data, because different samples might lead to different conclusions. We can't be certain that our conclusions are correct. Statistical inference uses the language of probability to say how reliable our conclusions are. And in the next supplement we're going to continue. So thank you.